Hello everybody. In the last video we did Newton's first law and we just did a little introduction. So we stated the law and looked at a few places where it could be applied. Now today we're going to look at more applications. So again, the law was an object will remain stationary or moving at a constant velocity unless acted upon by a net force. Now, like I said, this here outlines the cases where F net is equal to 0 newtons. Okay, and there were two parts that it underlined where it is either stationary or moving at a constant velocity. Those are the two cases which we know the F net is equal to 0 newtons. So let us look at an example. Okay, so this is complete the free body diagram. Magnitudes for the following stationary object. Now the object is stationary, which means that the F net is 0. Okay, and we must remember that there's two planes. We work in two dimensions. Okay. And if it's completely stationary, that means the F net in both of those dimensions are 0. Okay, so before we get along to that, let's draw it and then I'll explain what I've said. So here we have our inclination, so I'm just going to draw it again. Okay, so it's 30 degrees and here's our dot. Okay, so what force is always acting on an object? And that is your gravitational force. Like I said, if you are on Earth, on the moon, or on Jupiter for that matter of fact, there always is going to be a gravitational force pulling you down towards that planet or surface. So the gravitational force is downwards, and that is Fg. Okay, we also call it weight if you want to. It means the same thing. Now, in the case with an inclination, what is important to know is that we break up this gravitational force into its components. Now, the components of your gravitational force are F perpendicular. Okay, why is it called F perpendicular? Well, as you can see, it is perpendicular to the surface, and the other part is F parallel. Why is it called parallel? Because it is perpendicular to the surface. So let us go and see how we calculate those things. So the formula for let's start with parallel, is Fg sine of theta, where theta is the angle of the inclination. Fg is your gravitational force, so that's mg sine theta. Now let's substitute our values. The mass was 10 kilograms. The gravitational acceleration on Earth is 9.8 meters per second, and this is sine of 30. So substituting this into typing this into our calculator and getting the answer, this here is equal to 49 newtons. Okay, so we've calculated this. It is 49 newtons. So it said indicate with the magnitude. Okay, the F parallel is calculated in a very similar way. Sorry, I mean perpendicular. Just that we're going to use cos. So please guys, you need to remember the formula. So this is mg cos theta. So this here is 10 times 9.8 times cos of 30, which is 84.87 newtons, rounded off to the nearest two decimal places. So this here is 84.87 newtons. Okay, so how is this an application of Newton's first law? Is because we said this thing is stationary. So that means that there is something that is equal but opposite to these two forces, because if the force is in either of the direction, it should be moving in that direction. So what are the opposing forces here which are causing the net force to be 0? In this plane, we can assume it's friction force. since they did not give us any other values. And in this plane over here, perpendicular to the surface would be our normal force. Okay, what are the values of the normal force and the frictional force? Well, because the net force is 0, the sum of these forces must be equal to 0. So 49, so it should be 49 in this direction too, because it will be plus 49 minus 49, which will give us 0. And again, this one will also be 84.87 newtons, as these two also have to cancel out. So do you understand how we've applied Newton's first law here? On the basis that it was stationary, we knew that F net was equal to 0. And what was important here was to see that if it's completely stationary, both of the planes, so this parallel plane and the perpendicular plane, both of their net forces have to be equal to 0. Now, just a few tips. First of all, remember these formulas. If you would like to know how do you get these formulas, well, it's applying trig. This works out to a right angle triangle, and it's just applying trig and using your normal opposite over hypotenuse and adjacent over hypotenuse. But you can learn the formulas. That should be good enough. The second thing is that I should point out is if you are drawing a free body diagram, you are either drawing the components of gravity, or you're drawing the gravitational force. In other words, you cannot have all three of these lines. So for this to be correct, you can remove that. Okay? Or so something like this is correct because it has the gravitational force is written down in terms of its components. Or if you don't want to move the gravitational force, you can take away the components, and that would be a completed diagram. But please do not draw both. Or if you are drawing both, maybe make this a dotted line. Oops. Make it a dotted line to indicate that it is not actually a part of force. If you draw them both, you're counting for those forces twice. Okay, so let us move on to the next example. Okay, so once again, the question is complete a free body diagram of the following object moving at a constant velocity. Okay, so again, there's those words that the net force is 0. Now again, we've got an angle here. So how do we draw the free body diagram? Well, you could draw the force at an angle, so that's 500 newtons. But what I prefer to do, okay, is draw its components. So like how the gravitational force was broken up into the components, something at an angle is also broken up into its components. So this here has two components, and this here has got an x component. Why is this called an x component? Because it is on your horizontal plane. And it's got a y component. Why is this called a y component? Because it is on your vertical plane. How do we know that the y component is upwards? Because you can see it's upwards there. And how do we know that it's to the right? Because we can see this here is at an angle to the right. Okay. So how to calculate these components? Once again, they calculated using trig, but we use the formula that fx is equal to f cos theta, and that will be equal to, now this F is the force in the rope, so it's 500 cos of 60. Now, a thing to note is that the 60 must be the angle from the x-axis to the line. So in other words, if they give you this angle here, you'll have to take the complement of it. So we're going to calculate 500 cos 60, and that is 250 newtons. Okay, so the x component is 250 newtons, and then the y component we calculate with the formula Fy is equal to F sine theta, where once again F is the force in the being pulled at an angle, or the tensions they sometimes call it, and writing cos again, sine of 60. Again, please make sure that's the angle from the x-axis. Otherwise, you're going to get the wrong answer. So this here is 433.01 newtons. So this here is 433.01 newtons. Okay, so this here is moving at constant velocity, which means that something is opposing these forces so that the net force is 0. Again, we've got two planes, okay? So what other forces could be here? Well, we know that there's the gravitational force. I left out a bit of information. Let's just say this thing weighs 10 kilograms again. Otherwise, we won't be able to calculate it. Okay, so the gravitational force we know is m times g. So it is 10 times 9.8, which is 98 newtons. Now, clearly, this here isn't cancelling out. And my example is actually not that great. It's 100. Let's say it. Sorry, for purpose of this thing, I have to have the value correct. So let's say this weighs 100 kilograms. Sorry. Okay, so this here is m times g, which is 100 times 8, which is 980 newtons. Okay, so there's 980 newtons in the downward direction and 433 in the upward direction. This plane is not in equilibrium, as in the net force is 0. Okay, so what force is missing? You've guessed it. It's a normal force, because this object is resting on a surface. So we need to calculate the normal force. So we know that F net is the sum of the forces on the same plane. So it's Fg plus Fy plus Fn. Now, what happens when you have two directions? You have to take one direction as negative and one direction as positive. So for these calculations, I'm going to take upwards as positive. In other words, downwards is negative. So we know that the net force is 0 because of Newton's first law. It's in equilibrium, constant velocity. It's not moving in that direction. So here we have minus 980. Why is it minus 980? Because it is in the opposite direction, in our negative direction, plus Fy, which was 433.01, plus Fn, which we do not know, must be equal to that. So this is 0 is equal to minus 980 plus 433.01, which is minus 546.99 plus Fn. So the normal force is 546.99 newtons. 546.99 newtons. Okay. Are those all of the forces? No, we are still missing one in the x plane, in the horizontal plane, that's opposing it. So let's call it a frictional force. What will this frictional force be equal to? Well, it will be equal to the x component because it is moving at a constant velocity. Okay. So let's just recap this over this example with things that you should note. Okay, so the first thing is that this was given to you at an angle. So when we have things being pulled by an angle, we should calculate their components, the x and y components. These are the formulas for things being pulled at an angle. Please note that these formulas are different from these formulas. Look at the question, see if it is if it's on an inclination or it's being pulled by an angle, because there's specific formulas for each one. Don't just assume and use any formula with an angle in it. Okay? The second thing is that you're in the case, and this is a very important, people often forget about the vertical plane, but here we had that the force is being equal to 0, and here we can see the different components. So as long as it's on Earth, there will be a gravitational force. There's a y component from that tension force and a normal force since it's on a surface. So all three of these forces must be equal to 0. Why? Because of Newton's first law. And then that gives us the ability to solve for Fn, something we did not know previously. So now we know what Fn is, so we can complete it. Last bit that I have to just say is, once again, this question did want the free body diagram of the following object. Now, in your free body diagram, you either draw the components, so you leave that out, okay? So your free body diagram can look like that, or you draw the angled force. So your free body diagram can look like that. Do not draw them both. Okay? If you want to draw them both, draw either the components or the original one in a dotted line to indicate that it's being counted twice. Okay. Well, that's all of the questions that I've got for now. So please remember, this year's two very, very, very important concepts, and those are the concepts of objects on an inclination and the second one is objects being pulled by an angle. Okay, so please go over these examples. Make sure you understand how to break it into its components. The next video will be on Newton's second law, where knowing this will play a vital role. Thank you for watching. Please subscribe and tell your friends about these videos. Also, if you have any particular questions or would like the questions to be done in a certain way, or a particular topic in maths and science, comment in the section below. I will read them and I will do a video. Once again, thank you. Have a great day.